Hi everyone, in this video we're going to see how to price European options has call and put options with the Monte Carlo method in Python. So as usual, first of all, we rename our Jupyter notebook file, for instance, European Monte Carlo. And okay, now we can start writing the code. First of all, as usual, we need to import some packages. I'll write it as a comment to help you. So import first NumPy as MP, then the Yahoo Finance package. And if you're not familiar with this, I suggest to watch my previous video in which I explain you how to download live data using this particular package. And then from the datetime package, we import datetime and time delta, which we'll see later on why we'll need this. Okay, now we can pass to download the real market data from Yahoo with, as I said before, with using the Yahoo Finance package for Python. So first we create our stock name, for instance, the Apple, AAPL, then the end date, which is today. So we want to retrieve the data up to today, and the start date is exactly 1 year ago. So using the time delta function we have imports, it's end date, so today, minus the time delta of days equal 365, so 1 year. And so we have the end date is today and the start date is exactly 1 year ago. And now we can download data. So stock data is equal to yf.download of, and there are some inputs. The first one is the stock name, so Apple. Then we have start equal to our start date, and finally end equal to our end date. Okay, and I can print this data for you so that you can visualize them. Okay, and as you see, these are all the data starting from the 19th of November 2021, so exactly 1 year ago, and up to today, which is the 18th of November 2022. Okay, if you want to show just the last data, you can print .tail, and so you can see just the last 5 days. Okay, now we can pass to the next step, which is compute the stock volatility. So what we're going to do now is to take all the adjusted closure prices of the last year and compute the stock volatility. Again, I write it as a comment to help you reading the code. So compute stock volatility. Okay, first we have to compute the daily returns. So daily returns, which is stock data, which is our whole table. The column we consider is, as I said before, the adjusted closure column. So ADJ close. And then dot percentage change, PCT underscore change of 1. So it's the daily return is to understand for example, this daily return considering the 15th and the 14th of November, it's 150 over 148 and so on. Then we have 148 and so on. So here we have, for instance, plus almost 2%, and here minus almost 2%. Okay, then we have to compute the actual stock volatility, which is the standard deviation of the daily returns. So we have daily returns dot std, which is the standard deviation. Now we can print the result, for instance, daily, then we get the stock name, so daily Apple volatility, column, and we print our stock volatility. Let's see if it's correct, and as you can see, the stock volatility in this case is about around 2%. Okay, the daily volatility, of course. Then we have to choose our option parameters, so European option parameters. Okay, it's, for instance, as I said before, we're going to price call and put options, European options. So the stock price, of course, we are going to take the last value of our adjusted closure column of the stock data. So stock data of the column adjust close, and then -1, since we want the last data, which is today value. Then we have the strike price, and we consider it equal to the stock price since we're going to price at the money, in the sense that the strike price is equal to the stock price. Then we have the risk-free rate, which these days a good value could be 4%, for instance. And then the maturity of the option, which we consider, for instance, 1 year. Then we can print, just to visualize better this value, the stock price of today, which is stock price, and then our value of the variable stock price. And we can pass to the next one. As you see, it's the very same, 151.289, and it's the same value, of course, as we expected. And okay, now we can build our function to compute European option price with Monte Carlo method. Okay, we have to define this function. We call it, for instance, European option price. We want to return both the value. This function will be able to return the values of both the European call option and the European put option with the parameter given as inputs, which are the stock price of today, the strike price, the risk-free rate, the volatility, the maturity, the number of simulation for the Monte Carlo, and then a flag, which will tell you if you want the call price or the put price. But we'll see this later. Then column, and we can start creating our function. So Z is the random, the normal random the Gaussian variable, which represents the Brownian motion of the stochastic differential equation. Okay, so numpy as np dot random dot standard normal, and we want n simulation values. Okay, then we have the underlying forward value price, which is S0, so today's value, times the exponential, always as an numpy function, exponential of risk-free rate minus 1/2 times volatility squared, so V squared, times the maturity. And then we have the part regarding the stochastic part, so volatility times the square root of the maturity times our Brownian motion, so the random normal variable. Okay, now we have to distinguish the cases. So if the flag is call, sorry, without brackets, they're not needed here. If the flag is cool, then the payoff will be the maximum, always from a NumPy package, of S forward, the final price at maturity, minus the strike price, or 0, so the positive part. Otherwise, if the flag is equal to put, so the input, the player, let's say the user wants to price a European put option, then the payoff is equal to, I copy and paste this part, but we just need to invert the difference, so strike price minus the forward price. Otherwise, we know that we are not managing other flags, so we can just print, for instance, incorrect flag, and then we return in this case. And okay, otherwise we have to return the exponential of minus risk-free rate times maturity, all times the sum of our payoff divided by the number of simulations, so the average of our payoffs. Okay, and we have defined this function. Let's see if it's correct. For example, trying to price an actual option. So we set the number of simulation at, for instance, 100,000, and then we create this variable called price, and we call our function, so European option price of, and then we get all the inputs, which are first the stock price as 0, then K, which is the strike price. Okay, here I have done a mistake. I called it strike price. Okay, the strike price, then the risk-free rate, R, risk-free rate, then the volatility V, so stock volatility, the maturity of the option, which is 1 year, and the number of simulations. Finally, we write, for instance, here call. Okay, and then we print our result. We print call price and our variable call underscore price. Let's see, and as you can see, our call price with all the parameters we've set as input is $5.97. And to change it, it's enough to change the variable as put, and here we can set put price. Okay, we rename our variable, we rerun it, and as you can see, as expected, of course, the price of the European put option with the very same parameters as the European call one, it's very below the call, and it's exactly 0.047 cents. And that's it. And thank you for watching. I hope you found this tutorial useful, and see you in the next tutorial. And again, thanks for watching.